Hi everyone. Today's topic is heat transfer. So we will see which are the important topics. So we will have a quick revision on heat transfer subject. So in our chemical engineering heat transfer syllabus, the total weightage for GATE 2021 is, or normally in GATE your total weightage is 8. Out of that 8, you are having what totally 6 topics. Right? Out of the 6 topic, majority of the questions, if you see the last 20-year question paper, majority of the questions are from conduction plus heat exchanger. Majority in the sense almost 65 to 70% of the question in the last 20 years has been from conduction and heat exchanger. So whenever you do revision, right? So whenever you do revision, first you have to complete both conduction and heat exchanger, right? In a detailed manner, right? So that is because these two are the most important topics. Because if you see every year question paper, starting from 2001 to 20, every year there will be minimum one question from conduction, there will be one question from heat exchanger every year. Clear? So we'll start with everything, right? So then we are having topics like convection, radiation, boiling and boiling, evaporator, etc. So maybe in 2-3 years there will be a question from evaporator, right? 2-3 years there will be a question from condensation, right? But every year there will be one question from heat exchanger and convection. That is for sure, right? Out of this 8 marks. I hope that is clear. Now we'll start with conduction, right? So first chapter we have is conduction, convection. That is, you will be having questions based on conduction and convection, right? So first of all, in conduction, what are the law we are first studying, right? So the first law is obviously your Fourier's law of heat conduction minus Ka into dt by dx. So this is our first chapter where we are dealing with what? One-dimensional steady-state heat transfer, right? So we are not going into three-dimensional thing, right? Or unsteady state. First is our basic thing, that is one-dimensional steady-state heat transfer. Now, then you have what? Convection. The convection equation is what? HA delta T. Clear? So these are the two equations. So combining these two, you will be having what? Based on the steady state heat balance, you will be having a lot of questions. Clear? So you may have questions based on what? The combination of conduction, convection in wall and cylinder. Both questions will be there. For example, if you see, majority of the question from one-dimensional conduction are based on this composite wall. Clear? So this is your composite wall, that is this thermal conductivity is K1, this thermal conductivity is K2, length is L1, the length is L2. This is your constant area for heat transfer. One directional heat transfer, we are considering only X direction heat transfer. Clear? So this is the basic thing. So what is your heat transfer resistance for conduction? For a wall, it will be L by Ka. Clear? So this based questions will be there initially. That is, if you say here you are having temperature T1, here you are having temperature T3. Clear? So according to your steady state heat transfer, what is the meaning? Steady state heat transfer meaning is there is no accumulation of heat. Whatever heat is transferred from T1 to T2, same amount will transfer from T2 to T3. This is your basic thing, right? So based on this, if you are able to write whatever heat is transferred between T1 T3 will be what? T1 T3 divided by resistance is L1 by K1A plus L2 by K2A. The same value of heat transfer will be happening from T1 to T2, right? Because whatever heat is transferred from T1 to T3 is initially transferred from T1 to T2. So this equation we can write it as what? T1 to T2, the same heat is transferred. So what is the resistance between T1 and T2? It will be L1 by K1A. Clear? So this is our logic. I hope this is understood. Right. Then what is the specialty? Next case what we are saying? We are saying here outside we are having a fluid, hot fluid. Here you are having a cold fluid which is having a heat transfer coefficient H0, which is having a heat transfer coefficient Hi. For example, in this room, right? In this room we are having a hot air, for example, or outside it is summer, so outside we are having what? Hot air. So from hot air to cold air inside this room, through this particular wall you are having heat transfer. Simple equation, right? Simple thing. So whatever heat is transferred in this particular example, since we are assuming what? One-dimensional heat transfer, steady state heat transfer. So you should be able to write these equations. Now, if I am writing here T infinity I minus T infinity naught, I have to add what? I have to add two more resistances. That, right? That will be convection resistance inside and convection resistance outside. Clear? So this is the way we will be writing the equation. So based on this you are having what? Number of questions in GATE. Same concept. If you are able to write whatever heat is transferred from here to here, here to here, here to here, here to here, everything is same. Why? Because of our assumption steady state conduction. If you are able to do this, right, if you are able to write this, all questions in your conduction part can be solved. Right, if you start from GATE 2004 itself, right, so all questions are based on this. Clear? Then you have what? You have a type of parallel resistance type questions also. Clear? So in case of parallel resistance, what we need to do, right, that is this here it will be R1, take it as R2, take it as R3. Clear? So total resistance will be what? R1 plus R2 R3 divided by R2 plus R3. So this is the combined resistance of this parallel resistances. Clear? So if you are able to understand that, right, we will be able to solve every questions in conduction based on wall. Now you have what? Same concept, steady state convection through a pipe. That is, you have a pipe, inside you are having hot fluid. Clear? And you have thickness of the pipe is this much, and you have what? You have some insulation is there, right? So this is your insulation. Then outside you are having cold air. So from hot fluid, right, hot fluid to cold air, definitely there will be heat transfer. Clear? Definitely there will be heat transfer, and you will be having how many resistances? First cylinder you will have some resistance, then through the insulation you will have some resistance, then you will have what? Convection. Same way, inside you will have some convection. Again you have what? 2 conduction resistances and 2 convection resistances. If you are able to write the steady state equation, we can easily solve the questions. Clear? So based on this, you are having a lot of questions. Then you have what? Then you have equations to find critical radius of insulation. Critical radius of insulation for cylinder is K by H. So how are we finding this? Critical radius of insulation is the insulation radius at which your Q will become Q max, or your resistance will become minimum. So by substituting your resistance equal to minimum or Q equal to Q maximum, you can easily calculate the value of what? RC. RC for, that is your critical radius of insulation for sphere, it will be 2K by H. Clear? So these are the main first chapter questions you are going to solve. That is in our first chapter, that is in our conduction, definite conduction, that is our steady state one-dimensional conduction. Clear? So this is our first chapter. Now when we move forward, right, once this first chapter is over, right, so in this first chapter, they will always give you the value of H, thermal conductivity, etc. for the calculation, so it's not a problem. Now, in the next chapter, that is, we will have a new term called heat generation in a particular wall. For example, if you have, clear, you have a one-dimensional wall with heat generation inside, then you have to consider what? Our general 3-dimensional equation for conduction. So I hope you remember the general 3-dimensional equation for conduction. So if you know that, right, it will be simple, that is dou by dou x of K into dou T by dou x, plus you have to write it for y, you have to write it for z, plus your Q bar will be equal to what? Your rate of change of internal energy, that is rho Cp dou T by dou T. This is your 3-dimensional equation. If it is one-dimensional wall, your y-z terms will be cancelled out. If there is no heat generation, this term is cancelled out. If it is steady state, this term is cancelled out. If I am not considering the heat generation, what will happen? This term and this term is cancelled out. Now, this I can take it as flux. So the meaning is what? Differentiation of something is equal to 0. So that something inside that differentiation, that is your flux, will be equal to constant. That's why we are saying in one-dimensional conduction, you are having heat flux constant in a wall. In a wall, since the area is constant, your heat transfer rate will also be constant. So these things you need to understand. I hope that part is also clear. Clear? Then you have what? Right. Then you have next stage you are having what? You should be able to remember cylindrical coordinates. That is the same equation in cylindrical coordinates you will be having spherical coordinates. So better thing is, in GATE, in our chemical engineering GATE, maximum cases they will be asking only what? They will be asking this one-dimensional conduction only, right? One-dimensional conduction. So better thing is, remember this combined one-dimensional heat transfer equation, that is dou by dou r of, that is 1 by r power n, dou by dou r of k into r power n, dou t by dou r, plus your Q bar is our heat generation. It can be in a wall, cylinder or sphere, no problem. It is equal to, again you can write rho Cp into dou T by dot T. So this value of n will be equal to 0 for a wall, n will be equal to 1 for a cylinder, n will be equal to 2 for a sphere. Easy. Right, if you remember this, remaining it is okay, right? There is no need to remember all the three-dimensional equation in every coordinates, no. Just remember the combined one-dimensional conduction equation. Clear? So once you know this for wall, cylinder and sphere, you should be able to find what? The temperature profile in wall or cylinder or sphere according to the question given to you, according to the condition given to you. You should be able to derive the temperature profile. For example, right? For example, I am saying, right? For example, if they give you normally in GATE, in chemical engineering GATE, the type of question they ask is one-dimensional steady state conduction with heat generation problems. These are the maximum type they normally ask for us. So easy to write it. That is, you know the equation. If it is one-dimensional value, dou square T by dou x square, right? Plus heat generation means there will be Q bar by K. Steady state means here it will be 0. So you will be having what? Since it is one dimension, I can write it as d square T by dx square is equal to minus Q bar by K. So when you integrate this 2 times and you write an equation for T, you will get an equation of parabola. So then we will say if there is a heat generation, one-dimensional steady state heat generation in a cylinder, the whatever temperature profile you are getting will be a parabolic value, right? So for example, this will be your diagram. If you are having same temperature on both sides of the wall, your maximum temperature will come at the center. Clear? If you are having different temperature, your maximum temperature will shift either side. Clear? Next is what? Right. Next is sometimes they will ask you to find the maximum temperature point. Sometimes, right? That also you can do. Now they can ask one side of the wall is insulated. So whenever one side of the wall is insulated, you have to remember your maximum temperature will come at the insulated face. Clear? It will come at the insulated face, same parabolic shape, but the maximum will come at the insulated case. Now, if you remember, you have a GATE question where instead of heat generation, they have asked heat consumption. Right? Instead of heat generation, they have asked heat consumption. So in heat generation, T max will come at the insulated face. When in the case of heat consumption, what will happen? Here, your sign will become negative. So this will become positive. So second derivative is positive. So it will be a point of what? Minimum. Heat generation, your second derivative was negative. So it was a condition of maxima. That's why T max was coming at the insulated phase. If it is heat consumption, your second derivative is positive. So you will get what? Maximum. Instead of maximum, you will get T minimum at the insulated phase. Clear? So this is our almost the end of your first conduction chapter. Clear? That is basic, right? So basic questions they will be asking. Now once you finish this, you can go through cylinder with heat generation problems as well. Now, then you have what? You have the last part in the heat transfer conduction is unsteady state heat transfer. It's unsteady state heat transfer. It's very simple, right? That is, in this unsteady state heat transfer, we have the lump heat capacity analysis. Maximum questions so far from GATE are from only lump heat. When you are revising, first go through lump heat, then go for the other cases other than lump heat. That is, lump heat capacity analysis is valid when we have a very low value of Piot number. That is, our assumption is your complete temperature of the body is constant. That is, if you are cooling the body, initially the body is 100 degrees Celsius and we kept it in air at 30 degrees Celsius. After 5 minutes, right, if I am saying 98 degrees Celsius is the temperature of the body after 1 minute, I assume that complete body is at 98 degrees Celsius. That is my assumption for lump heat capacity analysis. Right? Originally it will not be true. Right? Originally it will not be true because all part of the body may not be at the same temperature, but in lump heat capacity analysis, it is our assumption. That is, throughout the body we assume at a constant temperature. So based on that assumption, we are going to find this kind of question they will be asking, that is, after 5 minutes, what is the temperature of the body? Or to reach this temperature, 37 degrees Celsius, how much time it will take? This kind of question. So for that you have the equation, right? T minus T infinity divided by Ti minus T infinity Ti is the initial temperature of the body, T infinity is our fluid temperature, is equal to e power minus HA divided by rho V Cp into T. If you remember your PDC, mCp divided by HA is our time constant. So e power minus T by tau. Same equation, whatever you have studied for thermometer in PDC, same thing. We are getting the same thing. So always connect it. Clear? So you may get the step change, right? So that equation is there, right? I hope you remember in PDC, you have studied this equation. That is your temperature minus temperature at steady state is equal to m is your step change into 1 minus e power minus T by tau. Right? So once you finish this particular revision class, so go back to our PDC, whatever we have discussed in PDC, right? And equate these two equations, you should get the same answer. Clear? So in both cases, what was the step change here? What is the step change in your PDC? Compare it and understand it. So that will be better. Clear? So you will have a better understanding. I hope that part is clear. So this is your end of conduction. Clear? So these are the total parts you have. These are the things you have to revise anyway. Right? That is, we may be having small other topics as well. They can ask from anything from conduction. But these are the previously asked questions. So first thing is you have to go through these topics for sure. Clear? So this is the part. Now, second chapter is what? Convection. So if we think about the equations or correlations, etc., convection is the most toughest. Convection has the most toughest equations to remember. Right? Lot of correlations is there. But for gate, this is going to be very easy. Convection part is the easiest syllabus we have. Clear? Because you have this equation, Q is equal to HA delta T. So far, whatever problems we have done in conduction, they will give the value of H directly. They will give H directly, no problem in conduction questions. Right? That is in our first chapter, conduction, convection mixed problem. Now in convection chapter, you have to find the value of H by using different correlation. Right? So for laminar it will be different, turbulent it will be different, because here we have a flowing fluid. Clear? In convection, you are having a flowing fluid. So here comes our connection with our fluid mechanics. Right? In our fluid mechanics, we are interested in finding what? Pumping power. For finding pumping power, we need the pressure drop. If you want to find the pressure drop, we need to first find what kind of flow it is, laminar, turbulent, etc. So for pipe, you have a separate equation. Your plate, you have separate equation. Same thing. Here, what you need to find? Here, you need to find the value of heat transfer rate. For calculation of that, you need heat transfer coefficient. For calculation of heat transfer coefficient, you need what? You need to understand whether the flow is laminar or turbulent, whether it is an external convection or internal convection. That is, external convection is flow over the plate. Internal convection is flow through the pipe. But in gate, chemical engineering gate, most of the questions so far asked are from pipe only. So far they haven't asked from plate. So better what you can do is go through the plate equations as well. Do one or two problems also, but you have to concentrate more on pipe, because most of the question, if you see from 2000 to 2020, all questions in convection are only from pipe. Right? For chemical engineering we are saying. Now we will see the equations you should remember for finding H. What is the first equation? That is, this is the first equation. Thermal conductivity of fluid into dt by dy at y is equal to 0 minus Ts minus T infinity. This is the first equation you have. Clear? This is based on what condition? This is based on the condition that we say when you have a fluid flow over a flat surface, first layer is not moving, first layer is stagnant. So whenever you have a stationary or stagnant medium, the heat transfer through that layer will be conduction. Clear? So we are equating the conduction heat transfer and convection heat transfer, and we are getting a value of H. And this equation is used, or this equation can be used only when we have a temperature profile. That is, when you have dt by dy or temperature as a function of y. What is y? Y is your distance from the plate. This is your y. Clear? Once you have a temperature profile, then only we will be able to use this equation. Now what are the other methods? Right? You have methods based on analogy, etc. is there. For plate, you have different methods, different equation. But what is important for us is pipe. Right? In pipe, you are having two conditions. What is the first condition? For example, when water is entering at a temperature Ti, it is coming out at Te. So if you have two different temperatures, definitely what should be the meaning? If you have two different temperature at inlet or outlet, the meaning can be only these two things. Either we had heat transfer to the fluid or heat transfer from the fluid. That's why there is a temperature change. Clear? That's why there is a temperature change. So this Ti and Te is your mean temperature at a particular cross section. Your mean temperature will change throughout. If the mean temperature is not changing, there is no heat transfer. Clear? So your mean temperature is changing throughout the pipe. That's why we are interested in heat transfer. If it is not changing, there is no need of heat transfer. Clear? So since you have only one fluid, right? Since you have only one fluid, you have only what? One energy balance equation, that will be mass flow rate of the fluid Cp into whichever higher minus lower. I am taking Ti minus Te. This is your first equation in convection in a pipe. If you remember, in heat exchanger you will have two fluids, that is hot fluid and cold fluid. So according to that you may have what? Two energy balance equation. M dot C Cpc delta T equal to M dot H Cph delta H, right, delta T. I hope you remember. Right, you have two energy balance equation. Why? Because in heat exchanger you are having two fluid. In convection we are considering only one fluid. Clear? Now, clear? This equation is always there. You can calculate, no problem. Now for calculation of H, you are having another equation, that is Q is equal to HA into, we will write this as Ts minus Tm. Clear? That is, what is Ts? Ts is the surface temperature of the pipe. Now you are having two cases. Second case is constant surface heat flux. If you have a constant surface heat flux, what we say is throughout the surface your flux is constant. If the flux is constant, your surface temperature will change throughout. So what will happen is your Ts minus Tm, this term will be a constant value. Now you are having what? Q. You have two equations for Q, and based on these two equations you can find the value of H. Easy, right? So if you have the value of H previously, right, before calculating this, you can find the area. So right, so based on this they can ask. Now the important question we have in GATE is based on constant surface temperature. If the surface temperature is constant, what will happen? If the surface temperature is constant, very easy. This Q will be equal to, it will become HA delta T Lm. Where are we writing? Why are we writing delta T Lm? Because this is Ts minus Tm average. So which is the suitable average for us in this condition? The average is, you can see here, initially my fluid is entering at 20 degrees Celsius. It is exiting at 70 because my surface is at 100 degrees Celsius, constant temperature. So you can see initially my difference is 80, finally my difference is 30. So here your delta T1 is 80, your delta T2 is 30. Now when you move forward in this direction, your temperature difference is changing. That is, your Ts minus Tm is not a constant, it is changing. That's why we are using what? An average value. I hope that part is clear, right? So for this one, the most suitable average we can use is HA delta T Lm. If you see the GATE question paper, you have 3 or 4 questions based on these two equations. Clear? So you know the equation how to find delta TLM. So whenever you calculate by using your virtual calculator, the thing you need to remember always in your mind is whenever you calculate LMTD, logically you should understand the value of LMTD. That is, here the logic is very simple, right? Everybody know that. That is, your value of LMTD should come in between 80 and 30. Clear? That is, your delta T1 is 80, okay? Your delta T2 is 30. So your LMTD should come in between 80 and 30. You should not get 155 as LMTD or 11.22 as LMTD, no. Right? If you are not getting a value in between these two, there will be some calculation mistake sometimes due to your virtual calculator. So you have to check it again. Right? So you should anticipate the values in GATE whenever you are solving. Right? So anticipation is very much important. Right? So you should know this much should be the range of the LMTD that I am going to calculate. Clear? So that understanding is very much important for the solving of these kind of questions. Clear? So this is what our convection, right? This deals regarding our convection. Now Last, one more correlation you need to remember, that is obviously your Dittus-Boytus equation. 0.023 Reynolds number power 0.8 Prandtl number power n. Or you can use 0.33 as well, no problem. So this is valid for what? Turbulent flow in pipe. Generally, they don't give you Dittus-Boytus equation in the question paper. You have to remember this equation. But other correlation, right? If you see laminar or different cases, you are having different correlation, right? In turbulent flow itself, according to the condition, you have lot of correlations given in your textbooks, like Sengel or Incropra. You have lot of correlation even in mechanics. But no need to remember any correlation. Only you need to remember whatever equation we have discussed so far for convection. Because if they are asking from any other topic, they have to give you the equation. Clear? So the point is, if they give you the equation, you should be able to solve and find the value of H by using that correlation. After finding the value of H by using that correlation, you should be able to find heat transfer rate. Clear? So this is your force convection, which is Nusselt number is a function of Reynolds number and Prandtl number. Then you have what? Natural convection, which is in that Nusselt number will be a function of Grashof number and Prandtl number. Clear? So you have to go through Grashof number equations, etc. But natural convection questions are very less so far in GATE. Or mostly whatever question they have asked is only theory from natural convection. Clear? So this is our first two chapters. So after convection and conduction, so next topic will be obviously radiation. So in radiation, again radiation, we have a very less number of questions from radiation in chemical engineering GATE. But it's a very big syllabus, right? So if you see radiation, there are a lot of topics are there in radiation. So follow whatever topics that are given in your MECAP, right? So only follow MECAP, because all the topics given in your Sengel or Incropra may not be needed for us. So whatever topics given in MECAP, so go through that will be better. So the important topics is obviously your Stephen-Boltzmann's law. Clear? So most of the questions are directly based on what your Stephen-Boltzmann's law, that is your black body emissive power is equal to sigma T power 4 multiplication by area. So these kind of thing. Plus majority of the questions from radiation, almost 75% of the question from your radiation is based on view factor. Right? So view factor calculation, most of the questions are based on two surfaces only. So for maximum questions are from based on two surfaces. There are three surfaces questions are also there. But most of the questions is solvable based on what this equation and what your F11 plus F12 plus etc. equal to 1. Right, most of your questions can be solvable with only these two things in your radiation. Then you have a topic called radiation shield, right? You have a topic called radiation shield. So based on radiation shield, that is if you have two parallel plates in between, we are inserting one radiation shield, that is to reduce the radiation between the two surfaces. So based on this also they can ask some question. Clear? So this is the total topics we have for radiation. So go through the questions as well, then you will understand what are the previous year questions they have asked from radiation. Then once conduction, convection, radiation is over, so the next topic you have is what? Heat exchanger. Basically in our heat exchanger, your total problems can be classified into three, right? So our first type of problem is your selection of heat exchanger based problem. Right? Selection of heat exchanger based problem. That is, if you see selection of heat exchanger problem is for a particular heat duty, we want to select a particular heat exchanger. That is basically what is the meaning of selection of heat exchanger? We need to find the area of the heat exchanger. For calculation of this or for this particular method, you have what? You have a method called LMTD method. Clear? So this is your selection of heat exchanger. Next is what? NTU effectiveness method. So in this method, what is the speciality? That is heat exchanger will be given to you. Right? Heat exchanger will be given to you. The question may be to find, right? Question may be to find maybe what is the outlet, right? Outlet temperature of this particular case, right? So based on effectiveness NTU. In GATE, so far if you see the last maybe 20 years, there is apart from one theory question, no question they have asked from NTU effectiveness, but there are some questions given in your books like Sengel based on NTU effectiveness for a safety purpose, right? So you can go through that question. It's very easy to solve also. Remember, you have effectiveness NTU based equation. One equation is there for counter current flow, right? Based on counter current flow, double pipe heat exchanger. There's one simple equation is there based on NTU and effectiveness. So remember that simple equation, because all the other correlations for NTU is very tough to remember. Clear? So that particular equation you need to remember, that is counter current flow, right? That is, which equation you need to remember is counter current double pipe heat exchanger when your ratio of capacity, that is C minimum by C maximum, when that becomes 1. Right, so that equation you need to remember so that it will be easier for you to solve, because that equation is very simple. So remember that equation. So based on that you will be able to solve question. Clear? So this is the first two types, and the last type is obviously what? Your shell and tube heat exchanger design. That is, they can ask basically what kind of question they can ask from this based on your baffle spacing, or again the topics based on what your baffle spacing or baffles or design criteria. That is basically what? Whenever we say baffle is connected to what? Your shell side heat transfer coefficient only. It has no connection with the tube side heat transfer coefficient. Even though the baffle is supporting your tube, right? Even though the baffle is supporting your tube, it has no connection with the shell's tube side heat transfer coefficient. It has connection with only shell side. Clear? Shell side heat transfer coefficient. If you can remember that, all questions based on design criteria can be solved. Clear? So it is not practical to remember all the design criteria, right? That is, so basically what you can do is, this heat exchanger part, that is shell and tube heat exchanger part, is not given in your reference books like Cengel or Incropra. So for that you have to read McCab and Binay Kadatta. These kind of books you can follow, right? Definitely. So theory part should be covered from these two topics. That is, you have lot of things, right? Triangular pitch, square pitch, right? What is the equivalent diameter of square pitch? So base questions are also there. Clear? If you remember these kind of questions, there will be question based on this. Now, these two, probability of these two is very small. If you see the total heat exchanger questions in the last 20 years, only 20% they have asked from these two. That is only one question from NTU so far, and maybe 5 or 6 questions from the design part. All the questions are from what? LMTD method. In that particular method itself, you have 3 or 4 questions based on what? Area of counterflow divided by area of parallel flow. Clear? So, or area of parallel flow divided by area of counterflow. So always you know this value will be greater than 1. Clear? So based on this, you have lot of questions in GATE. So if they are asking area of parallel flow by counterflow and there is only one option available out of the 4, if there is only one option available which is greater than 1, tick that, no problem. Clear? So this is the point. If there are more than one option, means you have to solve and find the answer. Clear? So this is, as I told, in convection we are having only one energy balance equation. In heat exchanger you are having what? M dot C CPC delta T and M dot H CPH delta H. Sorry, delta T. Clear? So you have two energy balance equation, and also you have what? Q is equal to UA delta T Lm. If you are having multiple pass, right? If you are having multiple pass, you can use what? Q is equal to U into A into a correction factor into LMTD. Right? So this, whenever we multiply this, we will consider a correction LMTD of counterflow. So for finding this correction factor, if you see our GATE previous year question, there are two type of question. In one question, they will directly give your value of F. In another question, you have to find the value of the correction factor from the diagram given. That is, you have to find the value of P, you have to find the value of R, then you have to find the value of F. Right. If you remember in your thermodynamics revision, I have explained that calculation of your compressibility factor based on what? Your reduced pressure and reduced temperature and that graph. Same way, by using the value of R and P, you should find the value of F. Clear? So these are the important topics you have, right? So these are the maximum type of question they can ask, right? So there are minimum, right? Minimum 15-20 questions are there, right? If you see the last 20-year paper, right? So based on only LMTD method answer. Right. There are other questions from design, that's not I am mentioning. Based on only LMTD, you have this much question. Clear? So this is the meaning in heat exchanger. So these are the total number of topics, total type of questions you have in heat exchanger. Now, once this is done, you have what? You have only two topics remaining. One is your evaporator, one is your boiling and condensation. So if you see boiling and condensation, in boiling and condensation, so far we don't have any problem. There is only one problem in 2019 where there was a question based on nucleate boiling, but that question can be easily solved by using what? Simple your energy balance equation, Q is equal to M into lambda, right? But no need to discuss that, but you have to go through what? Boiling curve. Right, boiling curve is important in this particular chapter. Clear? So only boiling curve is enough. Right, whenever you are revising boiling part, because we don't have problems in this boiling curve. Right, boiling chapter so far they haven't asked. This year they may ask. Clear? Next topic we have is condensation. Clear? In condensation, right? In condensation you have two type of condensation. Obviously, one is what? Dropwise and film-wise. Right? So in dropwise condensation, your heat transfer coefficient may be high, but in film-wise condensation, your heat transfer coefficient is low, but it is very difficult to have a sustained dropwise condensation. So we will normally study only your film-wise condensation. In our syllabus, we have only film-wise condensation. So what is the reason? I hope you know what is condensation. That is, you have a saturated vapor here, right? So the temperature of vapor is T vapor. Now we are bringing a solid surface which whose temperature is, that wall temperature is less than the temperature of vapor. Clear? So this is the meaning. So what will happen? This vapor will condense on this wall. Right? So whenever the vapor is condensing on this wall, you can see the thickness of the film is increasing. Clear? So this is your condensation basics. Now as I told, right, so when we go down in this direction, that is Z direction, so when you go downwards in Z direction, what happens to your film thickness? So this is your film thickness del. So your del will increase in the downward direction. Why it is increasing? Because more vapor is condensing. Clear? So due to the condensation of more vapor, you are having what? The thickness of the film is increasing. Now, if you remember the equation, right, or the correlation, so whatever after doing the total derivation, you will get what? Del is proportional to Z power 1 by 4. That is, your thickness of the film will be increasing proportional to Z power 1 by 4. If you see, this is laminar film-wise condensation on a vertical surface, right? If you remember in fluid mechanics, same way you have what? Laminar boundary layer thickness is proportional to what? X power half. Clear? So always whenever you study, so compare these things, these formulas, etc. So it will be easier for us to remember things. Clear? So del is proportional to Z power 1 by 4. And other thing, what is happening? Your heat transfer coefficient, that is local heat transfer coefficient, is proportional to, right? It will be proportional to, we can say, or it will be equal to, you can say, K divided by del, or it is inversely proportional to your film thickness. Why? Logically also you can think, because when you go downwards, your del is increasing, your thickness is increasing. When your thickness is increasing, what will happen? There is more resistance between vapor and the solid wall. Right? In between the solid wall and the vapor, you have more thickness of the film. So when the thickness of the film is increasing, right? Clearly, I hope you understood. That is, when the thickness of the film is increasing, what will happen to the heat transfer? You have more resistance, so your heat transfer will decrease. That's why you have a inversely proportional relation. Clear? So same way, you have the general equation, that is for H. You can remember that equation as well. Now, the thing you need to remember important is, sometimes they can ask this, average value of H is equal to 4 by 3 times heat transfer coefficient at Z is equal to L. This also you can remember. So based on this also they can ask question. They can ask the question based on the actual equation of H, right? So you have a total, you have an equation. So based on that also they will be asking one question, right? So that also you can remember. That is H is equal to, right? So that there is a long equation, right? I'm not writing that. I hope you remember that. You can see the book, right? So based on that question also they can ask from condensation. Clear? So this is the only topic we have in condensation, that is laminar film-wise condensation on a vertical surface, right? So clearly you can remember this. So accordingly they will be asking question. So this is about what? Your boiling and condensation. Now once you finish boiling and condensation, you have what? Evaporator. If you see evaporator, your questions on evaporator, whatever questions we had so far from evaporator is based on your general material balance, right? That is, you can see here, feed is entering into the evaporator at a temperature Tf, and we are sending in what? Steam. Steam is entering here, right? Steam is entering, and water will be vaporized, and thick liquor will be coming from the bottom. Right? Thick liquor will be coming from the bottom. So whatever heat we are supplying by the usage of steam, that Q is equal to what? Mass flow rate of steam into latent heat of condensation of steam, because from the steam we are giving a heat of Q. Now this is also equal to what? Right, so this particular value or whatever heat you are sending in, this will be equal to what? This will be utilized for increasing the boiling point of the feed, right? Not increasing the boiling point. What I am saying is increasing the temperature of the feed to the boiling point of the solution. That is, the heat given by the steam is utilized for increasing the temperature of the feed from Tf to boiling point of the solution, and also for the vaporization of your water. Clear? So whatever heat is given by your steam is utilized for changing the temperature from feed temperature to your boiling point of the solution plus vaporization, right? So we can say the mass flow rate of feed is m dot f, mass flow rate of vapor is m dot v, mass flow rate of thick liquor is m dot l, and your mass fraction is xf. Here if it is xl, then you have directly what? Material balance is very simple, that is m dot f into xf is equal to m dot l into xl. Because why? Because in vapor you don't have any solute, right? That is, your solute is not present in the vapor, it is only water we are vaporizing. Clear? So this is the equation you need to remember. These are the two equations you need to remember. And also you have what? Q is also equal to UA delta T, but delta T here is your temperature of the steam minus boiling point of the solution. In this equation, you have an effect of boiling point elevation as well. So if you want to learn more about boiling point elevation, why I am again saying boiling point elevation term? Because most of the questions from evaporator, other than this your basic material balance, have been from theory. Clear? So the questions based on capacity or your steam economy is there, but still your maximum type of theory questions before 2004 are from boiling point elevation. So if you want to learn more about boiling point elevation, what happens to the multiple effect evaporator with a boiling point elevation case, so that thing you have to read it from MECAP. Right? So it is only given in MECAP, right? I don't think in Cropra or in our reference books like Sengel, evaporator chapter is not given. So we can read it from MECAP or Binekadatta only. That is our chemical engineering books only we can read it. Clear? So go through this evaporator as well. So that is the end of your total 6 topics. Clear? Start with conduction and heat exchanger always, because that includes your 70%. Then go forward, your convection, radiation, then boiling point, boiling and condensation, and the last one you need to discuss is what? Last one you need to remember is evaporator. Right? So this is the pattern you need to follow. So based on this, you have to solve all questions from 2000 to 2020. Clear? So this is the total quick revision of your heat transfer syllabus.